Hey folks, here we are at lesson 7, where we're going to start making use of those reference frames that we defined in lesson 6 and begin looking at velocity and acceleration vectors. So think back to chapter 1 when we introduced a vector and we talked about position vectors, we talked about velocity vectors, and even alluded to acceleration vectors. And so when we did this, we had this idea of a reference frame, and then we had a vector that define the position of point P relative to some other point, which most of the time is the origin. Now, we've now expanded upon this, and we've started to define how we characterize these reference frames. And so this is reference frame I, which we all know as the inertial reference frame, and it has an origin of O, and then is defined by these basis vectors or unit vectors, E1, E2, and E3. These are orthogonal vectors, and this is our operational definition of a reference frame. The reason why we call them basis vectors is because any vector, in this case a position vector, that we're defining by coordinates within this reference frame, we're going to define as a series of scalars that are attached to each of these vectors. So it forms a basis for any other vector that's defined in that reference frame. And that's what we see here, where we have the position vector of point P with respect to O. It's a function of t, meaning that it's changing with time, and it's created by the scalar r1 in the e1 direction, the scalar r2 in the e2 direction, the scalar r3 in the e3 direction, and that's our position vector of point P with respect to O. Now, we don't want to stop here and just define the position of points relative to each other. This is dynamics. We want to see these things move. And so, to do this, we now need to define what is this time derivative of that vector. And so that's the vector that we see here that goes from point P to this future time in t plus delta t. And so it's this vector, which is a geometric quantity. Okay, and we've conceptualized this by drawing it on this diagram with our reference frame, but we need to get a working definition of this because we can't just be doing drawings and measurements. We can't pull out our ruler and actually measure this vector. Instead, we need to define the math around this so it's actually usable. And that's where this idea of the vector derivative comes into play. You've done lots and lots of scalar derivatives in all your pre-calculus, calculus, and all your math classes. But now we want to apply this to a real quantity. And so a vector derivative, in this case, is going to be the derivative of a position is going to be a velocity. And the derivative of a vector is a vector, so we need to create a velocity vector. So let's write it like this. We said earlier that the velocity is going to be the velocity of point P with respect to O, and our reference frame matters. So for any time derivative, we need to define what reference frame we're observing the motion, back to that conceptual definition from chapter 1. And this is equal to d dt, and this operation itself, we say, is performed in the inertial reference frame. And we're performing d dt on the position vector of P with respect to O. And so using the chain rule, this is pretty easy to write out, in which we say it's going to be d dt, as observed in the inertial reference frame, of the scalar r1 as a function of time multiplied times the position vector, the basis vector e sub 1, and then we need to have the next part of the chain rule, which is going to be that scalar r1 as a function of t multiplied times the time derivative as observed in the inertial reference frame of the basis vector e sub 1. So that takes care of this term, applying the chain rule. We need to do the same thing to the next two terms. So as we write those out, the time derivatives as observed in the inertial reference frame of r2 multiplied times the basis vector e1 plus r2 multiplied times the time derivative of the basis vector e sub 1, or e sub 2 rather, for both of these. And then add to this the time derivative as observed in the inertial reference frame of our scalar r3 multiplied times E3 plus the scalar R3 as a function of time multiplied times the time derivative as observed in the inertial reference frame of E3. And so that's our full complement of our vector derivative simply by applying the chain rule, which you guys have seen before. Now, we can make a simplification here. And the reason why we can make a simplification is because of our definition of this reference frame. Because remember, here, our reference frame I, our inertial reference frame, we said has an origin, which is a fixed point within the reference frame, and then we have these three basis vectors, E1, E2, and E3, which are all vectors that are fixed within the reference frame. So what that means is that we can then take the time derivative of our scalar, multiply it times that vector, and then the second term, the scalar multiplied times the time derivative of that vector, is actually going to be 0. Because the time derivative of something that's fixed within the reference frame, as observed in that reference frame, is 0. It's not moving in the reference frame. So each of these terms go to 0. And that leaves us with the velocity of point P with respect to O, as observed in the inertial reference frame, of this position vector is d dt, as observed in the inertial reference frame, of R1 as a function of t, multiplied times E1, okay, plus d dt, as observed in the inertial reference frame, of the scalar R2, E2, plus d dt, time derivative as observed in the inertial reference frame of R3 as a function of time along the E3 direction. And remember that a scalar, whenever we take the differentiation of a scalar, it doesn't matter what reference frame we take that in. So our velocity, v of p with respect to O, in the inertial reference frame, is r1 dot in the E1 direction plus r2 dot in the E2 direction plus r3 dot as a function of time in the E3 direction. Now keep in mind that in dynamics we're operating off of the Newton's second law, which says that F equals ma. And so we're not Aristotelian, so it's not F equals mv, so that means that we need to know the acceleration in the inertial reference frame to be able to solve our problems. And what's convenient about this is that if we have our position vector completely defined within the inertial reference frame, we've seen that all we have to do is take the time derivative of the scalars and then leave those with the same basis vectors they were already attached to. Well, the same thing holds for the acceleration if everything is already defined in the inertial reference frame. And so we just say r1 double dot as a function of time multiplied times e sub 1 plus r2 double dot as a function of time in the E2 direction plus r3 double dot as a function of time in the E3 direction. And so what we get here is a really nice expression of the first derivative and then the second derivative of the position vector. These are geometric quantities, these are both vectors in which we have the velocity and now the acceleration of point P completely defined now in the basis E1, E2, and E3 simply by taking the time derivatives of the scalars. Alright, let's see how far we can extend this concept. Let's say that we have another reference frame and we'll call this reference frame A. And A has an origin of O prime and then three basis vectors A1, A2, and A3. And so this is a separate reference frame. Let's say even that its reference frame is moving relative to the inertial reference frame. And we want to take the time derivative of point P with respect to O within the reference frame A. And so that means that we would write the expression of v, the velocity of P with respect to O, as observed in reference frame A. Now, we'll write this all the same way. d dt, as observed in the reference frame A, of r, P with respect to O. And then, let's start working out that first line, where we have d dt, in reference frame A, of r1 in the t direction, r1 as a function of t in the e1 direction, plus the scalar r1 as a function of t multiplied times the time derivative as observed in the a reference frame of e sub 1. And then we have lots more after that. Now, in our last vector derivative, in which we were taking the derivative with respect to, or as observed in the inertial reference frame, we were able to take this last expression here, we would take the first expression here and get a scalar derivative multiplied times the basis vector, and then this last term simply just went to 0. We just got rid of it simply because the time derivative of the basis vector as observed in the inertial reference frame was 0. But observe here is that for this first line we can still do the same thing, in which we get the scalar r dot, take the derivative of it, multiplied times the e1 basis vector. However, on this next expression, we have to leave this scalar intact, and then we have to leave this derivative intact. And the reason why is because e1 is not fixed within the a reference frame. And you can see that here, because in the a reference frame, this can be moving and twirling and spinning and accelerating. And if we're trying to observe this e1 vector, then its time derivative is not 0. But in fact, we have to figure out how to express that time derivative of that basis vector in order to calculate the time derivative as observed in a different reference frame. And so the point being is that the velocity as observed, velocity of p with respect to o, as observed in an inertial reference frame, is not the same as the velocity of p with respect to o as observed in another reference frame. Okay, that's a key thing to keep in mind, because we're about to start introducing multiple reference frames, and we need to understand how those reference frames cooperate and how they don't, and how to transform between them. All right, we're going to leave those transformations between reference frames for lesson 8, so that'll be the next one. For now, we're going to stay with our vector derivative, in which we're taking the derivative of the scalars and simply attaching those to each basis vector. So let's take this example of this sliding block P on this plane, or on this incline, and I want to walk through just how to define each of these reference frames in detail. So we're going to apply 3 reference frames to this, potential reference frames. The first one we're going to call an inertial reference frame, and that means that we're going to have our point O, and there's one leg of our reference frame. Here's the other leg of our reference frame. This is reference frame I, and so our reference frame I has an origin at O, and then we'll use the E1, E2, and E3 basis. And so we'll define E1 in that direction. We'll put our E2 in this direction. And then that means that E3 is actually pointing out to us. Now when we define each of these reference frames, we can't just put the basis vectors on there. We actually need to define their directions. And so this is the inertial reference frame with an origin at O, and then this set of basis vectors. And so let's be explicit here. So this is where E1 is defined as, and so I use 3 equal signs for that, or a 3-line equal sign. And so we're going to say it's defined as pointing to the right. And then we define E3 as out of the page, and then E2 is equal to E3 crossed with E1. Alright, so there's our inertial reference frame, or our first reference frame. So let's define our next reference frame. We're going to call this the A reference frame. So the A reference frame, put this in green, the A reference frame has an origin, we'll call it O prime. We'll stick with our convention in which we say basis vectors A1, A2, and A3. And we want to define this reference frame at this point O prime. And we want the A reference frame to be conveniently placed in which we have one of its axes along the incline. And so for this A reference frame, let's define its basis vectors as A1, and there's A2, and then A3 will be pointing out to us. So the A reference frame, where A1 is defined as pointing downward along the incline, A3 out of the page. Okay. Or another way we could say that is A3 is the same as E3. We're defining that. And then A2 is equal to A3 crossed with A1. Alright, so now we have two reference frames. And so for our third reference frame, let's create a reference frame. We'll put it in purple. This will be a reference frame in which our origin is at O, and then we have one of the axes going through the mass P, and then the other axis perpendicular to this. This will be our B reference frame. So B has an origin at O, B1, B2, and B3 are the basis vectors. So let's draw our basis vectors on here. We'll have B1 going through the mass that we're interested in, and then B2 is pointed 90 degrees from that, and so we define these more explicitly by saying where B1 is defined as the line from O to P, okay, because we're starting at the origin O and going through P. B3 is out of the page, and then B2 is B3 crossed with B1. So let's take a step back here and let's look at what we've done. We've defined three reference frames. We've defined the reference frame A, or reference frame I for the inertial reference frame, and so that's kind of our typical to the right up basis vectors. We've defined the reference frame A, and the reference frame A is along this incline and perpendicular to the incline, and then a reference frame B. And our reference frame B, notice this, the reference frame A and I were both fixed reference frames. The reference frame B, its first vector, basis vector B1, was defined as the line from O to P. So that means that as this block slides down the plane, that means that this reference frame B that has this basis vector B1 is going to be rotating. And it's going to be rotating the way we see it if the block slides down the plane. This reference frame is going to be rotating clockwise down. And so we now need to define some coordinates which are going to help us associate those reference frames with each other eventually. But right now, we're concerned more about defining the positions and defining the velocities of these within each reference frame. So let's define the position of our mass P within each reference frame. So to do that we need some coordinates. So in our inertial reference frame we are defining r of P with respect to O, because O is a fixed point within that reference frame. And so our coordinates are going to be an x coordinate, and we also have a y coordinate. Alright, therefore we can define r of P with respect to O as x in the E1 direction plus y in the E2 direction. Alright, so that's our Cartesian coordinates. Remember, we can also define this in polar coordinates within that reference frame. And for the polar coordinates, we need to have an r and a theta. And so r, defined as the distance from O to P, the direct distance, and then theta is the coordinate that's describing the angle of that radius, that radial line. And so then, in the same basis, r of P with respect to O is going to be r cosine theta in the E1 direction plus r sine theta in the E2 direction. And so we see it's easy to take the time derivative of these in the inertial reference frame because we're already in these bases E1, E2. And so what that looks like, if we're going to find the velocity, the velocity of P with respect to O in the inertial reference frame. In Cartesian coordinates, it's simply x dot in the E1 direction plus y dot in the E2 direction. In our polar coordinates, velocity of P with respect to O, as observed in the inertial reference frame, we need to use the chain rule, which is r dot cosine theta minus r theta dot sine theta, all in the E1 direction, plus r dot sine theta plus r theta dot cosine theta in the E2 direction. And so in both cases we're simply finding the scalar derivative of these scalars that we start out with, the scalar time derivative of each of these, and we're keeping the same basis, E1 and E2. Alright, and using our vector derivative we can also calculate the acceleration for each of these. And so the acceleration of P with respect to O in the inertial reference frame, in Cartesian coordinates it's x double dot e sub 1 plus y double dot e sub 2. Easy enough. Now in our polar coordinates the expression gets a little bit more complicated, and so using the chain rule once again, acceleration of P with respect to O in the inertial reference frame is equal to r double dot cosine theta minus r dot theta dot sine theta minus r dot theta dot sine theta minus r theta double dot sine theta minus r theta dot squared cosine theta, all in the E1 direction. And then let's take care of the E2 direction, and that's r double dot sine theta plus r dot theta dot cosine theta plus r dot theta dot cosine theta plus r theta double dot cosine theta minus r theta dot squared sine theta. And when we collect our terms, we simplify the expression a bit, and we get this expression in which we're able to combine a couple of our terms here in the middle. Alright, now this looks incredibly complicated. all this acceleration, because remember, we need to get our acceleration in the inertial reference frame in order to then apply Newton's second law, and this is the acceleration of point P in the inertial reference frame in polar coordinates. We'll apply that in just a moment to the simple pendulum, and we'll actually show how this makes our intuition and our life a whole lot easier by using polar coordinates. Before we move on, though, we need to address these other two reference frames that we have. We have reference frame A, and remember that reference frame A, to define the position P from reference frame A, we now need to define a coordinate that goes from O prime to position P. So let's just call that coordinate S. And so within reference frame A, we can say that P is defined by R P with respect to O prime, and that's it's a scalar S, and that's in the A1 direction. Now, reference frame A, if we take the velocity P with respect to O prime within reference frame A, our vector derivative is easy still. It's S dot in the A1 direction, and then the acceleration, P with respect to O prime, as observed in the reference frame A, is equal to S double dot in the A1 direction. So you can already see how defining a different reference frame makes this pretty easy. Okay, if we can define the position in a simpler way in a different reference frame, that's a good thing to do. Now we have reference frame B, and reference frame B isn't a reference frame that's fixed. Instead, it's rotating with respect to the inertial reference frame. And so for reference frame B, we want to define the position P with respect to point O. So it's R of P with respect to O. And you'll see that the position P with respect to O is simply going to be the distance R along the basis vector B1. So R is the scalar, B1 is our direction. So now that's our vector of P with respect to O observed in this basis. And our velocity of P with respect to O in reference frame B is R dot in the B1 direction. And then the acceleration of P with respect to O as observed in the B reference frame is R double dot B1. We'll start putting these into practice and making these alternative reference frames handy. All right, for now we're going to move to our simple pendulum again and look in terms of our inertial reference frame, define this in terms of polar coordinates, and define those equations. I was incorrect. We're going to do Cartesian coordinates first. So for this simple pendulum, first we need to define our reference frames, or our reference frame rather. We're going to define this as an axis pointing to the right, pointing down. This is our reference frame I. We'll have an origin O and E1, E2, and E3 basis. We're going to point our E2 to the right, our E1 down, E3 out of the page. And so let's define that specifically, where we say that E1 points down, E3 out of the page, and then E2 is going to be the cross product of E3 cross with E1. Put our direction of gravity, and then let's define our coordinates. And so for our coordinates, let's create x coordinate and a y coordinate. And now we're ready to define all the kinematics that we need for this problem. So first we start with the position vector, r of p with respect to O, which is defining the position of our mass. and that's going to be y in the E1 direction plus x in the E2 direction. We need to find our acceleration in the inertial reference frame, so we're going to take the derivative twice in the inertial reference frame. So v of p with respect to O is equal to, we'll write this all the way out, so d dt in the inertial reference frame of r p with respect to O. And so our basis vectors are already in this reference frame, so this ends up being easy. Y dot in the E1 direction plus x dot in the E2 direction. And then for our acceleration, p with respect to O, as observed in the inertial reference frame, we're going to do d dt observed in the inertial reference frame of our velocity p with respect to O. We always need to put our reference frame in which it's observed, and that gives us y double dot in the E1 direction plus x double dot in the E2 direction. Now in this system, we do need a free body diagram, so we need to draw the free body diagram of our mass. So the FBD is of the mass P, so draw our mass, and we need to put all the forces that are acting on this mass, and that's the force due to gravity, mg, and then we have the constraint force, F, that's holding our mass onto our pendulum, our massless pendulum. So those components, because we're working in this Cartesian, on the Cartesian basis, is this ratio y over L, and then pointing to the left, F with the ratio x over L. So we apply Newton's second law, and Newton's second law says the force, this is a vector, applied to point P is equal to the mass multiplied times the acceleration of point P as observed in the inertial reference frame. So we need to define these vectors. The force applied to point P, if we look here, then we have mg, and mg is in the positive E1 direction. So mg is pointing down, E1 is pointing down. That never changes. So we define this vector as mg in the E1 direction. Okay? So what's nice about this vector approach is that we no longer really have to keep up with what's positive, what's negative, how is this changing, how is this not changing. We simply look for the easiest way to describe the direction of a vector in the easiest basis. And so mg pointing down is always pointing down, it's always in the E1 direction. So that means that this force here, F scaled y, F of times y divided by L, there's our scalar, that's pointed up, and up is in the opposite of the E1 direction, so that's in the negative E1 direction. Our next scalar for our force, F times x over L, is pointed to the left as we see it, and so that's in the negative E2 direction, so negative E2. And that's our entire forces applied to point P. So we're going to set this equal to our mass multiplied times our acceleration of point P as observed in the inertial reference frame, which we see here. So it's going to be our mass times y double dot in the E1 direction plus the mass times x double dot in the E2 direction. Alright, so now we've got the vector expression for Newton's second law right here. So we collect our terms and then set our coefficients equal to each other. So collect our terms in the E1 direction, and this gives us mg minus f times y over L is equal to m y double dot. And then in the E2 direction, we collect our scalar terms, we get minus f times x over L. This is equal to m times x double dot. And so now we have, from one vector equation, we have two scalar equations because we're working in two dimensions. And remember, this is a 1 degree of freedom problem, 1 degree of freedom system, so that means we need a constraint equation, and that's x squared plus y squared is equal to L squared. And then we can differentiate that a couple times and then be able to now put this into this 1 degree of freedom system in terms of a single coordinate like what we did before. Alright, so let's take care of this simple pendulum in polar coordinates. So we've already defined our reference frames, they're the same, or our reference frame, it's the same. We do need to define our coordinates, and so we have the coordinate r, which is the distance from the origin to the point P, and then theta, which tells us the angle of that line. And so for our kinematics, we need to define the distance of P with respect to O, and that in polar coordinates is r cosine theta in the E1 direction plus r sine theta in the E2 direction. Now remember we have a constraint here, and it's a very convenient constraint in that our coordinate r is equal to L, which is a constant. So our point P with respect to O is L cosine theta in the E1 direction plus L sine theta in the E2 direction. And so when we take our velocity of point P as observed in the inertial reference frame, that's d dt in the inertial reference frame of r, P with respect to O, and so that gives us negative L theta dot sine theta in the E1 direction plus L theta dot cosine theta in the E2 direction. Our acceleration then, using our vector derivative, is d dt in the inertial reference frame of our velocity of point P as observed in the inertial reference frame. And so this expression is negative L theta double dot sine theta minus L theta dot squared cosine theta, all in the E1 direction. And then our second term is plus L theta double dot cosine theta minus L theta dot squared sine theta, all in the E2 direction. Before we can apply Newton's second law, we need to define the forces on the particle. We do that using our free body diagram. And our free body diagram consists of our mass P. We have the force due to gravity pointing down, or in the E1 direction. And then we have our constraint force, F. And we can break this into components, where our constraint force is negative F cosine theta in the E1 direction, okay, because it's pointing up and E1 is pointing down, minus F sine theta in the E2 direction, because as we've drawn this, it's pointing to the left and E2 is pointing to the right. Alright, so it's a matter of applying Newton's second law. And Newton's second law says that all the forces on a particle are equal to the mass times the acceleration of that point as observed in the inertial reference frame. And so we have all that information, so let's just put it in. So we get our force is mg in the E1 direction minus F cosine theta in the E1 direction minus F sine theta in the E2 direction. This is equal to our mass multiplied times our acceleration, and so this is negative L theta double dot sine theta minus L theta dot squared cosine theta, all in the E1 direction, plus our mass times L theta double dot cosine theta minus L theta dot squared sine theta in the E2 direction. So the last step is to equate our coefficients from the E1 direction and the E2 direction, and from that we'll get mg minus f cosine theta is equal to minus ml theta double dot sine theta minus ml theta dot squared cosine theta. And for the E2, coefficients that we pull out is minus f sine theta is equal to ml theta double dot cosine theta minus ml theta dot squared sine theta. And so with these two scalar equations, we can do some algebraic manipulation, and then from this end up with a single equation of motion, which is quite nice, in which its theta double dot is equal to minus g over L sine theta. So you can clearly see that the advantage of using polar coordinates, of going through all these derivatives, is that we get a really nice and simple expression for the motion of a pendulum. And so this is an equation that we'll use frequently, that you can memorize. Theta double dot is equal to negative g over L sine theta. And this is all that we need to know about the motion of a pendulum. So just to wrap this up, we have used our vector to define our reference frames, and then we've begun to solve dynamics problems, solving for equations of motion using our vectors. We define our basis, and then we define the location of the mass in our basis, and then we use our vector derivative to take the time differentiation to get our velocity in the inertial reference frame, our acceleration in the inertial reference frame, and that can be using whatever coordinate system that you want. We apply that using Newton's second law by taking our information from our free body diagram, and then we can develop our equations of motion. All right, see you in class.